Hello everyone, nice to meet you here. I'm Peng from Beihang University. My major is vehicle engineering. Today I'm glad to be here for sharing my research progress with you. The title of the report is on multi-sensor information fusion method for autonomous vehicle perception system. Besides, thanks for Professor Karimi's help and guidance, then this work can be completed smoothly. This work is classified into 5 parts. The first one is the research background. The second part is the research idea. Then I will mainly introduce the third part. It contains the camera observation model, data point cloud processing, sensor parameters, and sensor data synchronization mapping. In the last, I will show the simulation result and future work with you. Now, let me introduce the first part, research background. As we know, autonomous driving has recently become a hot topic in the automotive field, while low-level autonomous vehicles has gradually entered people's daily life. Based on the driving environment, the vehicle perception system can provide the real-time information for the autonomous driving. As a vital part of autonomous vehicle, the environment perception system can provide information about the driving environment for the autonomous vehicles. The driving environment is usually quite complex and is hard to be predicted. Thus, autonomous vehicles need to focus on the changes of the surrounding environment all the time. It's challenging to complete all the perception tasks with a single specific sensor. So, the sensors used in autonomous vehicles include onboard camera, LiDAR, radar, and millimeter wave radar. Compared to the other sensors, LiDAR has more advantages in obstacle detection and tracking. According to the running time of the laser, we can get the relative distance between the autonomous vehicles and the obstacles. Due to the high energy density and frequency, the laser beams can easily capture the contour details of the obstacles in the environment. Compared with the LiDAR, millimeter wave radar has no advantage in capture detailed information. However, its anti-interference ability is strong, so it is often used for sensing road conditions. The camera can express the surrounding environment directly, but it's hard to obtain actual depth information. Radar is cheap and has a long surface life. Because of low resolution, radar has significant limitation on acquiring dynamic information. Due to the racing requirements and cost constraint of the Formula vehicle, camera and radar are chosen for this project. As shown in the right picture, the autonomous vehicle is designed by Beihang. Now, let me introduce the second part, research idea. It's challenging to complete all the reception tasks with a single specific sensor. The second is, as the second combine of the LiDAR and camera can well identify surrounding vehicles and other obstacles. Autonomous vehicle sensing systems have begun to combine the LiDAR and the camera in recent years. Last, the LiDAR receives 3-dimensional space coordinate information, while the camera obtains the 2-dimensional plane coordinate information. To fuse this sensor data, the key is to establish a mapping relationship between the 3-dimensional space points and a 2-dimensional plane. These 3 are the research idea. Then, I will introduce the third part, research content. Through the principle of the optical imaging, the vehicle camera maps the coordinate information of the 3-dimensional space to a 2-dimensional plane, thereby realizing the image of the object. That is, the specific position of the camera in space is uncertain, so it is necessary to establish a spatial coordinate reference system to describe this mapping relationship. So this paper is introduced for coordinate system reference as shown in the upper right picture. Besides, the target under each coordinate system can scale rotated and translated to realize the transformation of the research project. The rotation transformation can be achieved by using a rotation vector through a three-dimensional vector. It can be shown as the Formula 1. We can see this. The R means the rotation matrix, T denotes the translation vector. Through the rotation matrix R and the translation vector T, the conversion relationship between the world coordinate system and the specific coordinate point in the camera coordinate can be described in the Formula 3. In order to simplify the corresponding between the camera coordinate system and the image coordinate system, it's assumed that the axis and the axis y of the camera coordinate system are corresponding to x-axis and y-axis of the imaging coordinate system respectively. Therefore, the corresponding relationship between the two coordinate systems can be described as the Formula 2. The corresponding relationship between the pix coordinate and the imaging coordinate can be obtained in the Formula 4. Besides, as the distance between the imaging point and the optical axis increases, the image magnificently increases, and is called the Peng decision. The processing of imaging decision is generally achieved by calibrating the camera's interparameters matrix. The A is the normal photo, the B is the barrier distortion, the C is the Peng distortion. This paper proposed a straight-through filter to pre-process the origin point clue data. The specific method is given as follows. First, define the coordinate system of the point clue data. Assume that the laser radar installation point is origin of the coordinates. The lateral direction of the vehicle is the x-axis. The longitude direction of the vehicle is the y-axis, and the vehicle direction of the vehicle body is the z-axis. According to the above coordinate system, the straight-through filter method limits the range of the point clue data. The point clue data processing is shown as the left picture, and the parameters of the camera and the lidar are on the right. According to the spatial synchronization method, the lidar and the camera are spatially synchronized, as can be shown in the first photo. The square paper calibration target is used and is hung vertically about 3 meters in front of the sensor. We can see a comparison diagram of the sensor used before and after spatial synchronization. The red color represents the contour of the object in pixel coordinate system. After coordinating conversion, the blue point represents the object contour combined by the laser radar, and then output to the pixel coordinate system. Among them, left one includes the fusion effect without spatial synchronization. Right one shows the effects after synchronization. It can be seen after the space synchronization, the object in the two coordinate system can achieve the effect of the overlapping. Based on the both space synchronization and time synchronization, the synchronous mapping of the lidar and the radar can achieve the laser radar point clue data is output to the camera data. The processing effect can be shown in the upper right photo. It can be seen that the sensor can not only work under a unified time and space reference, but also can identify obstacle information in the surrounding environment. So, the sensor spatial synchronization is mainly used to realize the uniform of the lidar coordinate and the camera pix coordination. The mapping relationship between the 3-dimension space coordinate system and a 2-dimension image coordinate is obtained by calibrating the camera's external parameters. Then I will introduce the conclusion. Target detection reference ability to accurately identify the type and location of an object through a target recognition algorithm. YOLO target detection treats the target detection problem as a regression problem, and then directly returns the position and the category of the bounded box in the output layer. Its advantage are the fast recognition speed and high accuracy, and it can be used in real-time system. So we use the YOLO algorithm to achieve the target algorithm. Above mentioned shows the sensor data was synchronized in time and space to complete the vehicle target recognition. However, the integration of data is not related to each other, so this data fusion needed to be processed. To solve this problem, we use the density-based specific cluster algorithm with noise to achieve the sensor-depth information association. This algorithm is a commonly used density clustering algorithm. The main idea is to divide the dense points in the L into the same cluster. It can realize the cluster of any shape without inputting category information in advance. Therefore, it can be used for the preliminary fusion data to realize deep information association. The experiment process is shown in this picture. The two color cones arranged are shown in this. These are blue and these are yellow. The data fusion of the sensor moving from the position 1 to position 3 is recorded, and 100 frames of fusion data of 3 observation points are respectively taken to obtain 300 sets of data. Visualization one group of data as shown in this. Above all, each data group contains 3 blue cones and 5 yellow cones with 2,400 recognition results. The data obtained from the statistic environment is shown in this table. And the table is called the confusion matrix. The sum of each row represents the true sample size of the category. Each column of the confusion matrix represents an accurate classification of the columns. The result shows its accuracy rate, which is 98.442%. Since the depth information in fusion algorithm using this paper comes directly from the major data of the ladder, and the distance error of the fusion data is consistent with the major error of the ladder. Moreover, the distance error is less than 2 centimeters. Therefore, the data fusion method proposed in this paper are highly accurate. The last one, we introduce the future work. In the future work, we will compare the accuracy of different algorithms and apply them to autonomous vehicles with these two sensors. We will apply this method to different actual situations. As to energy management, we will take the reinforcement learning into consideration with the connected cars. Strive to optimize the energy management. And this is all what I say. Thanks for your attention.